So I'm adding one more short presentation to this MDA 102 course, and it will deal with some glimpses towards how to integrate numerically. And again, it will be very similar to what we told about the differentiation. So we shall use the fact that the good approximation of the functions would be the Taylor polynomials. And so in fact, let's restrict ourselves to analytic functions, and we know how the integral looks analytically. It's again just the power series, which is obtained by integrating term by term, and we know that it just converges in a uniform way because it's continuous. That's something we already saw. So everything is supposed to work nicely. So you see, so if we just make something like a line, so it's A, B, and then I will have the intervals here. So what I do is I simply choose the points in the middle of the intervals, and I will have the jump in so the individual intervals will have length h, and so what you see, what we are doing is we simply integrate from minus h half to plus h half, and I name these things, I name them xi plus 1/2, because it's just the i's are to the red spots, right? So that's the chosen subintervals of our A, B interval. And now I have got the blue ones, which I call xi plus 1/2, and this is what's written here, and I integrate with respect to some variable, dummy variable t, so that's not interesting. But I can plug in the power series, I know how to integrate the power series, and so I see what is the result, right? So that's here. And now this is of crucial importance, because now we can think, well, so what shall we do? We shall integrate the most simple way. We imagine that simply we have the interval, and we have got the function here, and we shall have something like the piece here. So well, that's not very well chosen, so let's go to the skew one. So that will be our interval. So I have this point, and I will take the most simple approximation, this one. So I will have this trapezoid thing, and of course this is the same as if I take the point in the middle, as I am doing, and cut it here. So I simply take the representative of mine, will not be the real representative in the middle, but it will be the average of the two. And that's exactly what's written here, right? And now the rest is just a very straightforward and simple computation. So I approximate the integral by these trapezoids. So this will give me this, and compare with the Taylor expansion with the remainder. So I have got the estimates of the error. That's the main crucial point here. I know the estimates for the error. And now what I get is simply this. So you see, this will be, if I jump plus minus 1 2 times, which is exactly to come to the points, to the real points here. Then I get some estimate, then I get the expansion from the Taylor series, and so I get the estimate, because if I plug in the chosen PIs, then I get that it will be this plus something in the size of the error of 5th order. And so if I want to estimate what's the real error of this is just correct up to 5th order, right? And if I want to estimate what is the error for the single trapezoid, I just get this. So this will be the formula here. So that's the estimate of the error, which depends on third order of h and is multiplied by the second derivative in some point, and here is what kind of bigger error I get. And so if I sum it over all the subintervals, I get something which will be of this kind. And you see that it's n times, right? So you get b minus a times, it's constant, a square of our length of the norm of the splitting, and second derivative here in absolute value. So that's the upper estimate, right? So the norm is the supremum norm of the second derivative, and the remainder which remains here, which is the error, is already of fourth order. So you see, up to second order, this is the error we have to count with. And so you see that the trapezoid approximation of the integral is no way very bad, because it's exact in this. So the error is in the second order of the norm of the splitting, and it depends. So the implementation constant then depends on how big the second derivative might be. So for functions where the second derivative doesn't wiggle too much, we get good hold, and we can choose how small the h must be to get the precision we want to. Well, if the linear approximation here is, so this one is not enough, we can go one step further. So what about if we suppose that there will be the quadratic approximation? Then of course what we should do is, coming back to our plan, we would expect that the number of the intervals, subintervals here will be even, and we always take two of them to have 3 points, this one, and this one, which will help us to do with the second derivatives, right? Here we had to know only first derivative. If we want to approximate this in the second order, so we shall need the first and second derivative, potentially. So let's have a look what it means. So you see, so here you get the xi is now the middle of our double interval slot, and we have got the unknown constant alpha I and beta I. If I minus 1 come from here, and we want to compute the alphas and betas out of the f's, and we see that what we can do is to add them together, and then we have alphas gone and beta will be this. And essentially this is what we need, because if we then throw this into the integral, you see it goes from minus h to plus h, and so this term alpha it will not contribute at all, because it's just independent whether alpha is positive or negative. It will just cancel each other. It's first order, so it's an odd function, right? And so if I go from minus h to plus h, this one vanishes automatically. And so what I get as the contribution for the double interval in my choice is this. And now there is again a straightforward computation what it really is. So first of all it's this, and there was a British engineer, Simpson, who first, or seems first, at least the people name it after him, came up with this numerical way to integrate, and the entire integral is now approximated this way. So it's nothing complicated to implement. And now if you compute the error the same way as above, so you get that the error appears at the fourth order instead of second order, and again with the remainder of no interest of h5. But now it's just coming with the upper bound of the fourth derivative instead of the second derivative. So in practical situation, if you deal with functions where the fourth derivative wiggles way more than the second derivative, it might be more conceptual and useful to use the simpler approximation than this difficult approximation. And you can go over, of course, there are many other schemes which have some privileges and preferences in particular situations. So it's all then depending on the qualitative understanding of our data and knowing what kind of functions we want to integrate, and then you adjust the analytical methods. But as long as you deal with methods based on the Taylor series, we are roughly along the same lines as in the two examples I went through. So thanks, that's it for MDA 102 for this week.